graphically speaking, we know the derivative is the slope of the tangent line at a particular x. We run into some difficulty, though, with some graphs that have certain features. And that's what I want to look at next here, is where derivatives do not exist. Let's think about one in particular here. F of x equals the absolute value of x. Okay. V shape. Well, if I asked you, for example, the derivative at -2, that wouldn't be that hard, because all you got there, if you think about -2, is, well, you know, the derivative is the slope. Since it's a straight line, there would be the slope of that line. What's the slope of that line? Well, it looks like it's downhill, so it'll be a negative, and it's -1. If we thought about it a little bit. If I go over here to +2, what would be the derivative at +2? Well, derivative at +2 would be the slope of that line, which is the slope of that line, just 1. So the derivative would be 1. So a lot of this graph, no problem coming up with the derivative. However, we have kind of something different at 0, don't we? That's what I want to explore here. What about that derivative at 0? Because, I mean, one thing you can see, there's something going on there, because you got this slope coming in here, and then you got this slope coming in here, don't you? At 0. Well, if we look at it from the definition of derivatives side, f prime of x equals the limit as h approaches 0, f of x plus h, so that would be the absolute value of x plus h, plugging x plus h there for x, minus f of x, so it would be minus the absolute value of x, over h. Now we're talking about f prime of 0, so let's go ahead and plug in 0 there, because that'll make things a little bit easier to look at. So f prime of 0 would be the absolute value of x plus h, 0 plus h, sorry, minus the absolute value of 0. I just plugged in 0 for x. That's all I did. Well, this gets it down to something really we can think about here. You got the limit as h approaches 0. 0 plus h is h. Absolute value is 0, 0. So in the top, just the absolute value of h over h. Yep. Okay. Now, remember how we did the absolute value? Limits with absolute value. What we did was we changed h, the absolute value, we changed that either to, here's what it is. The absolute value of h is either minus h or it's h, positive h. Remember doing that with the piecewise? So this would be if h is less than 0, this would be if h is greater than, we could say equal to 0. So, here's what we've got. I look at, well, the limit as h approaches 0 from the left of this thing. Well, if h approaches 0 from the left, less than side of 0, I'm dealing with that, aren't I? Negative h. So the absolute value of h is negative h over h, which is negative 1, isn't it? Because the h is canceled, so you have negative 1 over positive 1. But what if you have the limit as h approaches 0 from the right? Well, that's from the greater than side of 0, so that's just h. So what do you get there? You get the limit as h approaches 0 from the right of h over h, that's just positive 1. So the limit from the left of 0 is negative 1. The limit from the right is positive 1. What is this meaning about this? does not exist, right? Which means, thus, what was this? It was the derivative. So the derivative at 0 does not exist. Proof that at this corner here, at the corner, that derivative does not exist. Okay? It exists anywhere else. Any other negative value, positive value, it only does not exist at 0. Now, what was special about 0 there? Well, it had a corner. Derivatives at corners, those don't exist. So if you've got a corner on a graph, the derivative at that corner does not exist. Okay? Same thing will happen at any corner on your graph. The derivative just will not exist. So that's, we can extend that out to any corner. Derivatives at corners do not exist. So if you've got a graph, wherever it is, and it's got a corner, so if I've got maybe one that has multiple corners, anytime you have a corner, so let's say that's y equals f of x. So that's 1, 2, and 3 here, okay? Let's make it consecutive there. F prime of 1 does not exist. F prime of 2 does not exist. F prime of 3 does not exist. Anytime you have a corner, the derivative there does not exist. Now the function value exists. There's a function value at 1. There's a function value at 2. There's a function value at 3. But the derivative at those corners do not exist because you run into the same problem. All right. Similarly, and I don't have time to go through it, but may show a little more about this, but there's a couple other places, let's say, where derivatives do not exist as well. Also, derivatives do not exist at discontinuities. And it's similar, I guess, to your corners, but good example here. Let's say that discontinuity there is at 3, the break. I think you can kind of see there that from the right and from the left, you got something different going on. It's obvious in this case. Yeah, so f prime of 3 here, you got to jump, got to break. The derivative does not exist there. You got discontinuity. That's the reason. Yeah, anytime you have a break like that, I mean, it doesn't have to be a jump discontinuity. I mean, it could just be a hole. At 2, still the same thing. Same thing. All right. And there's one other one. Again, we could do more to explain why, but here's the way I'll explain. All right, so let's say we've got that function there. All right? In this particular case here, if I think about the derivative at 2, derivative is tangent line. So if I draw a tangent line at 2, what are you seeing? Because that's so kind of flat, tangent line at 2, or what I meant for the tangent line at 2, it's a vertical line. Vertical line. Do you know anything about slopes of vertical lines? Slope of a horizontal line is 0, but the slope of a vertical line, undefined. You can't define the slope of a vertical line. Well, if the slope of a vertical line is undefined, and the tangent line here is a vertical line, guess what the derivative is? Undefined, does not exist? Yeah. Because you got a vertical tangent line. So that's the third one. Derivatives at corners do not exist. Derivatives do not exist at discontinuities. This is the third one. Derivatives do not exist when you have a vertical tangent. Vertical tangent. And those don't occur very often, let's say it that way. You could probably come up with a lot of examples, but as far as the functions we do, not very often. A good example, though, fairly easy example, is y equals the cube root of x. If you look at the graph of y equals the cube root of x, you got this kind of an S shape, I guess. But where do I have a vertical tangent there? You see? At 0. Okay. So you got a vertical tangent at 0. Thus, what's the derivative at 0? So f prime of 0 does not exist.